Well, hello everybody. My name is Boris Berenger. I'm from the UNSW node, and today I'll be chairing the session or this session on the International Mobility Program, IMP. So let me tell you a little bit about the program before we start. So this program gives opportunities for ECR and HDR to build their international networks and experience. The program supports research collaboration with international mathematical and statistical institutes, such as the Insight Center for Data Analytics in Ireland and the Network Center in the Netherlands. It also provides opportunities to collaborate with international visitors to ACEMS. So if you want to have more information about the program, you can go on the ACEMS website and have a look there. And if you log in through the portal, you can find the forms to apply for this program. So today we have three presentations. We have first Raiha Browning from QUT, and then Alexander Browning from QUT as well. And third, we will have Sarat Moka from UQ. So three presentations will be 12 minutes each, which will include questions. Okay, so first, I'm very happy to introduce Raiha Browning. So she's currently a second-year PhD student at QUT under the supervision of Kerry Mangerson. Her research is in modeling self-exciting stochastic processes known as Hawkes processes using Bayesian non-parametrics approaches. In her talk, Raiha will be presenting about work conducted from a collaboration that came from the IMP program. Raiha, the floor is yours.
Thanks, Boris. Is the sound okay?
Perfect.
Thanks. So as Boris mentioned, I'm a PhD student at QUT, and back in November last year, my clicker wants to work. There we go. So back when international travel was a thing, around this time last year, I went to the University of Oxford to work with Professor Judith Russo, who is an expert in Bayesian non-parametrics and asymptotics and cool things like that. And through this experience, I got to meet lots of cool people who are working on lots of interesting things, including Deborah Sulam, who we formed some like a working group of a few people who are interested in Hawkes processes, which I'll explain later. So that working group includes my supervisor, Kerry Mangerson, Judith, and one of Judith's other colleagues, Vincent Ravois. And so to start with, I'll explain what a Hawkes process is. So it's a self-exciting stochastic process. And so this means that, I guess, if you have like a Poisson process, the events are actually occurring independently from each other. However, in a Hawkes process, events that have happened in the past actually influence future events. And so there is this dependence on the history of the process. And this is really useful for a lot of applications like modeling neuron spikes in the brain, things like social networking, so modeling retweeting kind of behaviors, and things like earthquakes and stuff, it's also really useful for. And so through this working group, we were really interested in seeing if we could apply Hawkes processes to model the current coronavirus epidemic. And so to start with, we consider a few different countries that were severely impacted by the virus. We also have to make some modifications to the model because there is quite a significant behavioral difference as the epidemic progresses. And so we basically, for all of these countries, we look at when the maximum number of events happened. And so before that peak, we call this phase 1, which is that initial phase of exponential growth. And then after the peak, we call this phase 2, where the non-pharmaceutical interventions and things like that have started to become effective, and the number of events is actually going down and beginning to stabilize. And so here I'll introduce what a Hawkes process is, in particular a discrete time Hawkes process. So we have a number of events on a particular day y, and this is generated according to a Poisson distribution with a rate lambda, which is, this lambda is kind of what characterizes the Hawkes process. And so lambda is made up of two components, as you can see in this equation for it here. So the first component mu is like the baseline mean of the process. So this isn't really considering any of the previous events that have happened. It's just like what you would expect the process to go along by if there was no influence from those previous events. And the second term is the self-exciting component. Alpha is essentially a magnitude parameter, which tells you the expected number of offspring from a particular parent event over the entire course of the time. And this summation sums over all of the previous events that have happened before a time t. And we give that some kind of decay function, which is denoted by g, depending on how long has elapsed since those events. And in our model, we give g a geometric kernel. So this has parameter beta in it. And so if we look at the results, so I forgot to mention that lambda actually represents the expected number of events on day t. And so we put lambda against the observed data. So the observed data is the black dot and lambda is the red ribbon. So the ribbon is actually the 95% confidence interval of lambda, given our posterior samples. And it actually follows really closely to the observed data, which is really cool. And it's actually, it can accommodate for kind of abnormal behavior to some level. And so there's a lot of kind of weird dips and stuff, and the model can actually follow along with those pretty well. And yeah, so it's really reactive to the actual observed data. And then looking at the actual baseline parameters to start with. So the baseline parameters are those baseline means. And we can see that this mu1 is the set of parameters for the first phase, and mu2 is the set of parameters for the second phase. And so we can see that this reduces from the first phase to the second phase, which is kind of expected, but it's also probably due to things like reduced mobility, so people aren't really going out as much anymore, and also kind of a transition from imported cases, which would kind of represent this baseline process, so they're just occurring sporadically. And more of a transition into like community transmission, which would influence the self-exciting component more than the baseline component here. So moving on to the self-exciting parameters, alpha, which is our magnitude parameter. In the first phase, alpha 1 is greater than 1, and in the second phase, alpha 2 is less than 2. And so this is a significant result and also kind of expected, because if alpha is greater than 1, it means that the process is non-stationary, so it'll just keep kind of exploding out to infinity if you let the process run along for long enough. Whereas in a magnitude parameter less than 1 actually says that the process is stationary, so it will eventually just kind of stabilize and then follow along around that baseline mean. And there are also similarities between alpha and things like reproduction numbers, but they're not really directly comparable just because of the different frameworks that these two kind of approaches are based on. And lastly, we have the beta parameter from the geometric kernel. So we look at the inverse of beta here because that's the mean of the geometric distribution. And in general, the geometric kernel kind of describes in a way the influence of past events as time goes on, which we'd kind of expect to decay. But we can see that the mean of the geometric actually, in general, is larger in the second phase, which kind of indicates that the time between events is getting longer. And we speculate that this is probably due to, again, people not going out as much, so there's less opportunity to actually infect people, hence the time between infections is actually stretched out. And yeah, that's the basic outline of what we have found in this study. There's some other model checks and things that we did, but that's the kind of fundamental results. So we find one of the main outcomes of this study was that this discrete time Hawkes process, which is a really kind of simple model, is actually really flexible and is good at describing this really complex process. So we apply these models at the country level, and each of these countries were affected differently by the virus, and they also had different response measures and the timing of these. So there's a lot of kind of hidden interactions, and complexity that we don't actually model, but our simple model is actually able to kind of fit this and accommodate for some level of variability as well. So we also find that we obviously do need to kind of consider different phases independently, but we don't actually fit a complex change point model. It's actually just a static number, we don't estimate it. And we find that this still does a pretty good job at modeling these distinct phases. And it gives us like a comparison of kind of the different phases and the dynamics and the differences in that. And just as a final point, which is very important, we're not trying to replace the kind of standard epidemiological models, but rather we're just kind of seeing how we can look at it in a different lens to get some alternative insights. And yeah, we have a preprint on medRxiv at the moment, and that's all I wanted to say. Thanks.
Thank you, Raiha. That was a great talk and really good timing as well. We can now welcome our second speaker, who's Alexander Browning. So let me introduce Alex. He's also a PhD student at QUT, and he works at the interface of applied mathematics, statistics, and experimental science. So as part of the IMP, Alex visited Prof. Ruth Baker at the University of Oxford to establish a project that considered identifiability for SDE models in biology. So in today's talk, he's going to provide an introduction to identifiability analysis for models in biology. Alex, the floor is yours. Thank you.
Hi everyone, my name's Alex from QUT. I'm going to talk about my experience going on the IMP. First of all, I'd like to say I'm really grateful for the opportunity from ACEMS to go on the International Mobility Program, particularly as a PhD student or maybe an ECR perhaps. It was really great to kind of meet people in other universities in other countries and kind of see how they do mathematics. Yeah, so as part of my experience with the IMP, I went to visit Ruth Baker at the University of Oxford. So I'd met Ruth a couple of times at conferences and workshops and things like that in the past. So it was great to go and work with Ruth. So Ruth's interests are very similar to me. We both work in mathematical biology. We both are interested in stochastic models or SDE models. And we both are interested in inference techniques, including things like approximate Bayesian computation. So because the UK is quite small, I also was able to use the opportunity of being in Oxford, which is quite central, to get some cheap train tickets and go to visit some other people that I'd met at conferences and workshops and things like that in the past. So I gave a couple of talks and kind of met, hopefully, possible future collaborators at a couple of other universities around the UK. And it was really good to see what kind of things they're doing in mathematical biology over in the UK. So the project that we were interested in originally was actually looking at inference for stochastic differential equation models. But on the way to doing that, we sort of realized there was a kind of more fundamental problem that was sort of unanswered in terms of inference for stochastic differential equation models. And that's a question of identifiability. So in the talk today, I'm going to kind of provide an introduction to what identifiability is and perhaps why we should care about it. And then I'll kind of hint at the things that we look at in our preprint, which are to perform analysis of identifiability for SDE models in biology. So I've got an example model here. So this is a beta insulin glucose circuit. So we might use this if we're a clinician, say, and we're interested in diagnosing whether somebody has diabetes or not. So in this model, we've got beta cells which secrete insulin in response to a glucose concentration. And we're going to say that we're going to use this model to interpret some measurements that are of only the beta cell concentration and the glucose concentration. So we're going to say that we don't have the tools to measure the insulin concentration. So we might need to use our model to identify, say, two parameters. Maybe we're going to identify the insulin secretion rate, theta1, and the insulin sensitivity, sorry, theta1 and theta2, in order to diagnose whether this patient has diabetes or not, let's say. And I've shown an example solution of a deterministic version of this model down below. You can kind of see that there's actually two solutions. There are two solutions for two completely different parameter values. And you can see that they're actually indistinguishable unless you look at the insulin concentration. But because we don't measure that, we say that these two parameters are actually structurally not identifiable from this model, from those set of measurements. So to unpack this a little bit more, I'm going to take a step back and go to a simple model. So in this model here, we've got, say, an experiment called a cell proliferation assay, where we're observing cells divide, proliferate, give birth, and we're also observing cells potentially decay and die. And we can model this with a birth-death process, and we might be able to write down this as an ODE that looks like exponential growth, and then we can write down the solution. Now you can sort of see what's going on here. You can see that our two parameters in our model, theta1, the birth rate, and theta2, the death rate, actually only ever appear together. So it looks like our model, our deterministic kind of dynamics here, depend upon only the net growth rate or the difference between these two. So theta1 and theta2 are actually structurally not identifiable even in this really, really simple model as well, because we can't distinguish growth from, or birth from death. We can only identify the net growth rate. So to assess structural identifiability for a model like this, or perhaps more complicated ODE models where you can't just see it, we use an open source software called DAISY. So here's a DAISY import file here, and essentially DAISY lets you input your dynamic equations, so your ODEs, and what you observe, and you run it through DAISY, and a couple of seconds later, it tells you whether your model is identifiable or not. And it does some kind of heavy mathematics, so it looks at characteristic sets, and I think it uses differential algebra to determine this, but you don't need to understand that to be able to use DAISY and assess identifiability. Now, when you calibrate an ODE model like this to data, we're actually making some assumptions. Typically, we assume that noise is extrinsic and comes into the process because of measurement error. And if you've ever worked with experiments, you'll know that there is some measurement error there, but there's also a lot of sort of intrinsic noise or intrinsic noise that creeps into the data. So I've shown some example realizations of some data here, and these are actually exact measurements of this process. And you can see that the data is actually not deterministic. Our process is stochastic. So what if the noise contains information? So we might think that we could interpret this with an SDE model, say. So we've sort of got our long-term trends, our deterministic component of our growth up in the equation at the top, sort of to the left there. But we also capture variability, in this case, under some assumptions with a Brownian motion. And we can see that that depends upon theta1 plus theta2. So it sort of looks like from this SDE model, we should be able to identify these two parameters uniquely if we look at the noise as well. But there are actually no standard techniques to assess identifiability of SDE models directly. So what we do in our preprint, and we go through this for a couple of different examples, we write down a system of ODEs that describe the statistical moments of the SDE. So you can see here we've got M1 that relates to the mean. Now M2 relates to the variance. And then we can input these into DAISY, and DAISY will indicate for us that actually these moment equations are structurally identifiable. And we use this as a surrogate model for our SDE, and we make the conclusion then that our SDE model is actually structurally identifiable. So there are actually sort of two questions of identifiability that are considered in the literature. There's structural identifiability, which we've looked at so far, and that looks at features of the model that allow you to identify things. So sort of in some kind of limit where you've got infinite noise-free data. There's also a question of practical identifiability, and it's what really can you practically expect to learn given some kind of finite amount of possibly very noisy experimental data. And I'm sort of more interested in practical identifiability because I guess you could say it is more practical. We never have infinite data, and our data is never noise-free. But actually, to be practically identifiable, you first need to be structurally identifiable. So it's good to assess structural identifiability first before you go on to assess practical identifiability. So there's a figure, that's why I opened it in Chrome and we had issues at the start that doesn't appear here, but you just have to bear with me, and I'll say that I'm going to run through an example of practical identifiability of some observations from a birth-death process where I've got 10, I think, noisy time series observations from 10 different independent experiments. And we assess practical identifiability through an inference technique like MCMC. So I'm actually going to use particle MCMC here for our SDE model. And if I can come over here and I can use the mouse to point, you can see if we look at the ODE model, our theta1, theta2 parameters for our birth-death process, we see a region of the likelihood space that is equally likely. So we don't know where on that curve we actually lie, and we can't distinguish that based upon our deterministic model. But if we look at our stochastic model, you can see that we actually now identify the sum of θ1 plus θ2, and we can determine where on that curve we lie. So the SDE model, we might say here, is also practically identifiable as well as structurally identifiable. So identifiability is really requisite to effective inference. So we set out in our project to look at efficient techniques for inference for SDE models, but then we realized something that's very important to inference, and we decided to look at identifiability instead. So we demonstrate in our preprint that you can apply existing techniques, like for analysis of ODE models, through the moment equations to assess identifiability of SDE models. So if your model is structurally not identifiable, you either need to move to a stochastic model, which might capture more information, or you might need to simplify it. If your model is practically not identifiable, you might need to increase the amount of data that you've got. Now, if that's not possible, if it's not possible or it's very expensive to go and do more experiments, let's say, you might also simplify your model down in order to better capture the dynamics. So you can download some Julia code to assess practical identifiability and some DAISY code, as well as the preprint from my website. And that's all I have now. Thank you.
Thanks a lot, Alex. Same as Raiha, that was a really good talk and good timing. I really appreciated the fact that you took advantage of the program to also go and see some other researchers that were not far from Oxford. I think it was really good initiative. Are there any comments for Alex?
I can see University of Technology has a blue hand for us.
Okay, so UTS.
Yeah, it's Matthias Keras here from UTS. So thanks for a very nice talk. So I was wondering if you can use prior distributions to achieve this identifiability that you're talking about, if you put prior information on the parameters.
Yeah, so you absolutely can. So in our analysis, we actually take a Bayesian approach. So we incorporate prior knowledge. However, to some extent, you're very right. You can actually also rectify non-identifiability using prior knowledge like that. And that's more a feature of practical non-identifiability than structural non-identifiability. So you might actually conclude then that if you know more about your process from a model than you already knew from prior knowledge, you might make a conclusion then that, you've got practical non-identifiability from the data and model that you're considering. So you can identify really anything if you've got strong enough prior knowledge, and we sort of incorporate that using our Bayesian approach. So does that answer your question?
Yes, thank you very much.
Thanks, Matthias, for a great question. There is also a comment from Jason White in the chat, so I can read it to you if you want, Alex. The method of looking at moments can then have the problem that there may not be an upper bound to the number of moments you have to consider. The Taylor series method had this problem. In general, looking at the first n terms of an expansion is not useful unless it shows the model is structural identifiable. Otherwise, the result is uncertain, may change if you consider more terms.
Yeah, absolutely. So there's two comments on that. So if your model is really simple or it's linear like the birth-death process, your moments are exact. So in theory, yeah, so if you observe from the first two moment equations that it's not identifiable, you might go to the third and see that it's identifiable. In general, the problem with that is that observations of the moments typically become harder to get as the moments get, or the order of the moments get higher. So your observations of third order moments are typically more noisy than lower order moments. Another point is that, so this analysis doesn't give some kind of concrete conclusion. It's sort of more of a practical guide, I suppose. But people have actually looked and they've sort of found that for chemical reaction networks, the first two moments can actually be shown to contain most of the information anyway. So you're right, you might have to really, in theory, you have to look at all of the moments to be able to reach a definitive conclusion of identifiability or not. But people sort of think that most of the information is actually contained within the first two anyway. So this we think is sort of, I guess, a helpful tool nonetheless.
Cool. Thank you, Alex. That was great. I can give you a round of applause. Okay, so now it's time to introduce our third and last speaker for this session. We have Sarat Moka. So Sarat is a postdoctoral research fellow in the School of Mathematics and Physics at UQ. He obtained his PhD in system science from the Tata Institute in Mumbai. His research interests broadly lie in applied probability with a specific focus on Monte Carlo simulation. In particular, his research focuses on spatial point processes, perfect sampling, large deviation theory, and variance reduction techniques in Monte Carlo simulation. Today, Sarat is going to talk about Raiha event simulation for random geometric graphs. Floor is yours.
Thank you, Boris. Hi, everyone. I hope you can hear me and you can see the slides.
Yes,
Good.
Yeah, good. So this, under this IMP program, I visited University of Ulm to work with Professor Volker Smith. And while working with him, I took this opportunity to actually work with Christian Hirsch also when he was in Germany. So this work consists of both of these results. Some of it is ongoing, and Dirk and Thomas are from University of Queensland. They have been contributing in this. Okay. So in this talk, I will be first looking at what graph we are going to see in this talk. That's called Gilbert graph. And for the graph, what are the rare events we are going to discuss. Then I will present three methods. First is very simple naive Monte Carlo method, and then the method we developed with Christian, that is conditional Monte Carlo. And then finally, final method is importance sampling, which is something ongoing. Okay, let's begin with defining what is Gilbert graph. So consider you have a spatial point process on a window you are observing. Let's call it W. Point process is random point process is a set of points randomly generated according to certain distribution, but we fix what is the distribution. We call a point process is homogeneous Poisson point process if the number of points is a Poisson random variable with expectation lambda into volume of this window. So this lambda is called intensity, and for each n, the points are uniformly generated on this window independently. It's a simple process. This is a kind of reference point process for us. When we define Gilbert graph, what we do, we take these Poisson points as vertices in the graph, and we say that there is an edge between 2 points, say x and xj. If the distance between these 2 points are less than a fixed value r, without loss of generality, we can actually assume that r is equal to 1. This is the Gilbert graph. And what are the rare events we are asking for this? So let's denote this Gilbert graph with g of x, which has vertices coming from Poisson point process, and edge is defined with parameter r, which is taken to be 1, and the Poisson point process is intensity lambda. And throughout the talk, we denote the number of edges by just taking mod. It's not number of points, it's the number of edges in the graph. We are interested in estimating probability of event where number of edges being less than a level parameter called L, denoted with L. Typically, this is much smaller than expected value, expected number of edges in the Gilbert graph. That's where it becomes rare. So you can't really use naive simulation and simply estimate it. And that's why we would like to have a more efficient simulation methods. And equally, one can ask what is the probability, how to estimate these probabilities when n is much higher than average number. That is also part of the research, but in this talk, we ignore that part. Okay, how do we do it in a crude Monte Carlo way? Simple, you initiate, you have number of iterations, and for each iteration, you generate a number of points in the on the window, and generate them, generate those number of points uniformly and independently, and see whether this event is happening or not. This is the target event. And you take zero and one random variable, Bernoulli random variables, and take average of it. It's a simple way to compute any kind of probability of any event. But obviously, like, it's very naive way to do it, and we can definitely do a better thing. That's what is leading us to next method called conditional Monte Carlo. Notice that these points x1 to xn can be generated in any order. Most likely on a single process computer, we generate them in sequential manner. This is the proposed in the paper, which is now preprint is available. Let's simplify the notation by taking Poisson PMF by Qn, where this is the total number of expected number of points in a Poisson point process. So this is just denotes the PMF for the Poisson random variable. And x1 to xn is a fixed n, is a sequence of points generated independently and uniformly, and we denote with a small n. Today I say that there are n number of points. Then if you notice the probability which we are trying to estimate, if you write, this is summation over all the Poisson random variable taking n, and then generate uniformly and independently a number of points and check this whether number of edges in the graph are less than one or not. It's an expectation of infinite summation. If you define m to be the, like when you are generating these points sequentially, after at one point, you see that the number of edges in the graph are exceeding L. So you stop just before that. And if you define that variable, that number to be number of points generated to C before you see more than L edges, if you define it to be M, then all we are saying that probability of L is just a summation of these PMF terms corresponding to Poisson random variable. So it becomes easier if you know M, and you just need to compute the CDF of Poisson random variable at M, and just take average of that. So this is called conditional Monte Carlo method, and this is much better than earlier approach. Here we have summation, CDF is involved, and you take IID samples of this CDF by generating IID samples of M, and you essentially have an estimator, new estimator, which is much better than the naive Monte Carlo method. But can we do better? That's a question we started asking, and because we have seen that this conditional Monte Carlo in certain regimes is not working so well. So it's based on small observation that if you have a random variable, which is a Bernoulli random variable corresponding to event A with probability P, if you have another random variable which takes values between 0 and 1, also has the same mean. then obviously this random variable L has lower variance than the indicator random variable. So this is observation, because in this sum, the indicator random variables can be replaced with L, a sequence of better variables with better variance. And that is what we do. We introduce a change of measure. We denote with P tilde, and can we come up with such change of measure so that when likelihood is involved, we can have a better variance. And then you can compute under the change of measure, new estimator. How do we come up with this change of measure? Just suppose we are looking at L is equal to 10. We don't want more than L edges in the graph. So L is 10 here in this example, and you already generated certain points. Okay, here there are 10 points, but number of points is not relevant to L. We already see 7 edges formed here. Once we see, then you can think of each point is center of a sphere with the distance 1. And if you notice, this black region where if you select any point here, next point, it will create 4 edges because it is occupied with this is covered by four spheres, 4 points. So any point you select here will result in 4 more edges. Since you already have 7 edges, if you have 4, it's not going to satisfy the event. So you identify such regions, you avoid and keep on generating points sequentially. This is difficult to compute this region. So what we can do, we can use grid and approximate this region and generate the point. That is importance sampling, and there are certain theoretical results which we can't cover in this talk, but what we can see that importance sampling measure is always better than conditional. This is better than naive. And if you see simulation results, this is naive. You can see relative variance. It increases drastically, whereas conditional is better. If you compare with importance sampling, this is importance sampling too good. And similarly, for a different window, earlier was 10, and this is now 20. You can see that even conditional Monte Carlo is takes a lot of variance, but whereas importance sampling is much better. And yeah, that's about my talk. And
Sarat, I may have a small question.
Yeah.
Like what you presented was always presented on a 2-dimensional space.
Yeah.
Can it be in higher?
Yeah, you can have any dimension. It's the same thing as long as you can construct the grid. And
I guess the effect of the grid is, or you take that into account, or you just
so where the simulation in 2-dimension for this example, you can the complex like running time compared with conditional Monte Carlo is 2 to 3 times more. That's it. And I think we can improve more. I'm doing it in my way. I think it should be done much efficient way.
Okay, that's great. Thank you. Any final comments from anyone?
Thank you all.
Well, yeah, thanks, Sarat. That was great. Yeah, I guess this concludes the session for the IMP, and we can see that there is great research that has been done through the program, and that each of the participants have been able to also establish some research network. So I think that was great, since it's the purpose of the program. Yeah, so if anyone has any question maybe related to how to apply You can also contact some of the presenters if you want some tips on how they did their applications and things like this. Otherwise, you have information on the ACEMS website.